Okay, so for the following circuit, we have to find the filter type for the circuit and then calculate the cutoff frequency. So to calculate the filter type, you're going to need the transfer function, which will be VO of t all over VI of t. So let's first get the impedance values of all of these. So this is JWL, this will be just R, and this will be 1 over JWC. We'll plug in the values at the very end, okay? So let's first get the impedance equivalent to find VI of t. So let's combine the capacitance and resistance. So it'll be 1 over R plus 1 over JWC, which is just JWC, to the power of minus 1. And this, we can rewrite this as the following. Okay, this is the same thing as that up there. And that will just be 1 over JWCR all over R. And we can put this back into here, and these are the minus 1 up here. We can just flip them. Okay, and then to find the impedance equivalent, we just add this to the very end. So it'll be R over 1 plus JWCR plus JWL. Okay. Now to find the voltage VI of t, it should be equal to the impedance equivalent times the current passing through here. So let's call this I. So we just times this by I, and that's our VI of t. Now, we know VO of t is pretty much so we know since this is the ground here, it'll be 0 volts here. That means VO of t should be the same as here. And since this is one whole node, this area should also be VO of t. And since this is the ground, that means the voltage at this resistance should also be VO of t. So if we were to combine, sorry, hold on, there. If we were to combine these two, the voltage up here should still not change because there's no resistors or anything here interfering our path. So that means the voltage here will be VO of t. Here this is the ground, so that means the voltage difference here is also VO of t. So to solve for VO of t, it's pretty much the impedance load here, which is R over 1 plus JWCR times the current passing through that load, which is just I. The same I as this one. Now we can find our transfer function. Which gives us R over 1 plus JWCR times I all over R over 1 plus JWCR plus JWL times I. This and this cancels each other out. So it'll be R all over 1 plus JWCR all over R all over 1 plus JWCR plus JWL. Now let's times all of this by 1 plus JWCR, and same with this. And we get a more cleaner looking transfer function. And this will be equal to R all over R plus JWL minus W squared RLC. Okay, so this is pretty much what our transfer function is equal to. Now, this is how we're going to determine our band filter type. So there are 4 band filter types: low pass, high pass, band pass, and band stop. So this is the graph of a low pass one. So on this axis, it's pretty much like a Boyd plot. So this is the transfer function, and this is omega. So when omega is 0, our transfer function is at 1. And then as we go on, as omega goes to infinity, it starts slowly decreasing. Okay? And and when there's a ratio of 1/2, that's pretty much your cutoff frequency. Okay? Now for a high pass, when omega is 0, our transfer function is 0, but as we begin to increase to omega infinity, our transfer function also begins to increase. Okay? So it increases all the way up until 1. Oh yeah, and this is 1 up here, sorry. When omega is 0 for low pass, our transfer function is 1. For high pass, it's 0, and as omega goes to infinity, it reaches a saturation point at 1. And there's a cutoff frequency when the transfer function is at 1/√2. Then there's bandpass. So pretty much a bandpass graph, when omega is 0, our transfer function is 0. Then as omega begins to increase, we start slowly increasing up until we hit our cutoff frequency. And then when we are at our cutoff frequency, omega starts decreasing again, and up until then it goes back to 0. And when our transfer function is 1, that's when we get our cutoff frequency. And then for band stop, when omega is 0, our transfer function is at 1, and then as we start slowly decreasing, and then we start increasing again. So that means our cutoff frequency will be, when our transfer function is at 0, that's when we have our cutoff frequency. Alright, so we have this following transfer function. Let's take the limit for when w approaches 0. Okay, so for hw, so that will be r over r plus, oh wait, sorry, we should not quickly do that yet. What we should first do is pretty much get the magnitude of this first. Okay, so to get the magnitude of hw, we just get the magnitude of this first. So let's get the real components on one side, and then get the imaginary components on the other side. And then the magnitude of this will just be okay, and we just incorporate that here, and I guess we will just include these two bars at the for our hw. There we go. Now we don't have to work with any imaginary values. So let's take our limit when w approaches 0 for our magnitude of our transfer function. So we see this would be 0, this would be 0, so it'll just be r all over the square root of r squared, okay, which is just 1. And then if we take the limit as w approaches infinity for our transfer function, let's see what we have. We see this goes to infinity, and then this goes to infinity as well. This is just 1 minus infinity, but then we also add this infinity here. So this will just be over infinity, which will just be 0. And now we see the low pass one matches this. So this is actually a low pass circuit. Okay, so the next part we want to find is find the cutoff frequency. So we know the cutoff frequency will happen when our transfer function is at 1 over square root of 2. So R minus W squared RLC squared plus WL squared. Okay, so pretty much we just have to solve for the W here, and that will be our cutoff frequency. So what we can do is times this by the power of 2. Okay, let's bring this to this side, and we'll bring this to the other side. Okay, so then we just FOIL all of this out, and we should get this very long thing. We should get R squared minus 2 W squared R squared LC plus W4 R squared L squared C squared plus W squared L squared equals 2R squared. And this, let me continue. So it'll be W4 R squared L squared C squared plus W squared L squared. I'm just rearranging it right now. Minus 2 W squared R squared LC 2R squared minus R. So I just bring this to the other side, and that's just 1R squared. Oh wait, yeah, sorry, 2R squared minus R squared, and that's just 1R squared. Okay, now let's divide everything by R squared. So it'll be W4 L squared C squared plus W squared L squared R squared minus 2W squared LC equals 1. Let's bring the 1 to the other side, so it'll be minus 1 here. Let's see, let's factor out the 4 plus, let's factor out this as well. Wait, there's a W squared in both of these, so we'll factor it out from both of them. Minus 1. Okay, now we know the values of L and C. L should, so we know, okay, so L and C, L should be 2 Henry, and C should be 2 microfarads. Let me double check. Yep. So we just start plugging them into here. So it'll be 4 times 2 times 10 to the power of minus 6 squared plus W squared 4 over the resistance. What was the resistance? I think it was 2000, right? Yeah, 2 kilo ohms, so it's 2000. So 2000 squared minus 2 times 2 times 2 times 10 to the power of minus 6 minus 1. And this simplifies to 1.6 times 10 to the power of minus 11 W to the power 4 minus 7 times 10 to the power of minus 6 W squared minus 1. We're going to let T equal W squared. So it'll just be T squared and then T here. Now we can use the quadratic formula to solve for this. And using the quadratic formula, you should get T to be equal to 550,942.056, and T is W squared. So you just square root this, and you should get your cutoff frequency to be the following.